Okay, 3.34 part A, find the momentum space wave function phi for the nth stationary state of the infinite square well. I'm just going to start off by writing the position state for the infinite square well, which we should already know by heart at this point. Psi of x comma t is equal to the square root of 2 over a multiplied by sine of n pi x divided by a times exp of negative I n squared pi squared h bar squared, or no, not squared, divided by 2ma squared. Multiplied by time at the end, and this is going from 0 to a, where this is the width of our infinite square well. So if we want to find phi, then it's just going to be a matter of plugging this into a Fourier transform, in which case phi is going to equal 1 over square root of 2 pi h bar times the integral from 0 to a of e to the negative ipx divided by h bar multiplied by, let me just make that h bar a little bit neater, multiplied by our psi wave function, which I'm just going to copy down here. And then closed off with a dx, right? So, okay, immediately I'm dealing with a very complicated dx integral. Let me move as much stuff out of here as possible. This term obviously can move out because it's just a constant. This term has no x dependency, so it can move out. So I'm left with phi is equal to, the 2 cancels out here. So what I'm left with is 1 over square root of pi h bar a, and then multiplied by the complex exponential, exp negative I n squared pi squared h bar over 2ma squared, multiplied by time. And now our actual integral that we have to solve, integral from 0 to a e to the negative ipx divided by h bar times sine of n pi x divided by a times dx. Okay, now at this point, you have an integral where you have a product of a complex exponential with a sinusoid. So you have two options here. Option 1 is to convert the complex exponential into a sinusoid and solve a sinusoidal integral. Option 2 is to do the opposite and convert the sinusoid into a complex exponential. I would rather do the latter, because if I converted the e to the negative ipx to a sinusoid, I'm going to deal with a sine and a cosine, and I'd rather not have to do a two-step into a u sub. So instead, I'm going to convert the sinusoid into a complex exponential by invoking the rule that sine of x is equal to e to the ix minus e to the negative ix divided by 2i, in which case our phi term is now going to equal, just make that a little bit neater, there we go. I'm going to copy paste over the constants at the front, and then our integral from 0 to a e to the negative ipx divided by h bar. And then now let's see, so this implies that 2i sine x is equal to e to the ix minus e to the negative ix, right? And our x is going to equal, well, I don't really know why I did that, actually. I'm sorry. It's not really a point for me to convert that because I'm not converting the opposite way. This is going to equal, let's see, our x is n pi x over a, so e to the I n pi x over a minus e to the negative I n pi x over a, all divided by 2i, closing the integral with a dx, right? Minus e to the negative I n pi x over a over 2i. Yeah. Okay. Now let's further take out the 2i so that we're just dealing with this term multiplied by this term, right? So now what I'm going to have is phi is equal to 1 over 2i square root pi h bar a. Copying this over. Whoa, I don't want to cross that out. Copy that like this. And then I have my integral from 0 to a now of, let's see, e to the, let's actually just write it as exp to give myself a little bit more space. This is going to be negative ipx over h bar plus I n pi x over a multiplied by exp, or not multiplied by, minus exp of negative ipx over h bar minus I n pi x over a, closing this with a dx. Okay, so is there any way for me to simplify this down a little bit, right? This has a common factor of I, it also has a common factor of x, in which case what I'm left with is negative p over h bar plus I, no, not I, n pi over a. Similarly here, this has a term negative I and x multiplied by p over h bar plus n pi over a. Is that correct? Yes. Okay, now let's write that out fully. So now we know phi is equal to, and then let's copy this whole thing over again. Exponential of ix negative p h bar plus n pi over a minus exp of negative ix times p over h bar plus n pi over a. Okay, now we have an integral with two complex exponentials. We can split them into two different expressions, right? Because this is a plus term that's connecting these two complex exponentials. This can turn into two integrals, or you separately evaluate each individual complex exponential. So let's label these as 1 and 2. Now, for number 1, let's see. I'm going to have to start by combining this. So now I have exp of ix times what? Negative pa plus h bar n pi divided by h bar a. Like this, and this is an integral. So this goes to, I want to take that out, so this becomes a reciprocal. The integral of this is going to give me h bar a over I times negative pa plus h bar n pi, like that. And then I'm going to be multiplying it by the exact same expression, in which case, let's just copy paste this over. And this is getting evaluated from 0 to a. Let me just double check my work here. This is a very messy expression. H bar a, I negative pa plus h bar n pi, exponential I x negative pa plus h bar. Yeah, that's correct. Now, if I plug in 0 here, then this is just going to be a complex exponential of 0, which is just 1, right? So this is going to give me, and I'm going to factor out the h bar a over I negative pa plus h bar n pi at the front, just because that's a constant, right? So what I'm left with is a complex exponential of, let's see, if x becomes a, it cancels with the a at the bottom. So now you're just left with I times negative pa plus h bar n pi divided by h bar. And then you're subtracting it by the case where x becoming 0, in which case the whole exponential becomes 1, like that. Similarly, for number 2, let's also write that out fully, right? So this is going to be an exponential of negative ix times pa plus h bar n pi divided by h bar times a, in which case its integral is going to be negative h bar a over I times pa plus h bar n pi multiplied by the same complex exponential, in which case I'm just going to copy paste again, evaluated from 0 to a, in which case this is going to give us, let's see, same thing as before. I'm going to take this part and factor it out as a constant. And then on the inside, if x is equal to a, you're dealing with an exponential of negative I times pa plus h bar n pi over h bar, because the x becomes an a and cancels with the a at the bottom, subtracted by 1, because if you, once again, if you substitute x with 0, this becomes an exponential of 0, which is just 1. Okay. Next, let's actually plug this into the above, because now that we've solved the integral, we can rewrite it out, right? I am going to copy paste this. And then now you are going to multiply by h bar times a over I negative pa plus h bar n pi exp of I negative pa plus h bar n pi divided by h bar subtracted by 1. And then we are going to subtract by this term. So if we're subtracting, because we're subtracting by expression 2, and the expression 2 already has a negative at the front, 2 negatives make a positive, this is just going to become add h bar a over I times pa plus h bar n pi at the bottom, multiplied by the exponential. Oh, actually, you know what? I just realized I miswrote this. This should be this minus 1, like that. Because the minus 1 is not part of the exponential. And in that case, I'm going to have to change this into curly brackets to avoid further confusion. There we go. exp of, what's this, negative I pa plus h bar n pi divided by h bar subtracted by 1, close this bracket off, and then close the full bracket off. Am I correct? I think I am. Yeah, okay, so now I can, you know, distribute out the h bar times a over I, because that's common to this term and this term. So if I move it out of the expression, now I'm dealing with, let's see, it becomes negative at the top, because the two i's cancel at the bottom. So now you have h bar a times 2 square root pi h bar a, like that, right? And then same thing with the complex exponential. And now we're going to multiply 1 over negative pa plus h bar n pi. And actually, you know what? Let's make this a little bit. For now, I'm going to, just to avoid having this negative at the front, because I don't like the look of it, I'm going to say h bar n pi minus pa. Maybe that order will change later down the line, depending on how the sinusoids end up simplifying out at the final solution, but for now we'll leave it this way to just make it look a little bit nicer. Same exponential, so I'm actually, let's just copy paste that and clean it up a bit, like that, and then delete that, and then plus 1 over, to make everything nice, h bar n pi plus pa, like that. And then same thing with the exponential while closing off the bracket. Then let's erase that. There we go. Okay. Now at this point, you're going to have to simplify this super annoying exponential, right? So let's see. I'm going to have this in blue this time because I'm going to be working exclusively with this expression, right? So let's start by, I'm trying to think of like which way to do this would be less painful. Let's start by combining the two bigger fractions by multiplying h bar plus a and h bar minus a. In which case, so your bottom term, so you're going to have, let's see, this same exponential expression multiplied by h bar n pi plus pa, and then you're going to add this expression you're going to multiply h bar n pi minus pa, and then at the very bottom you have the combination h bar n pi minus pa times h bar n pi plus pa, like that. And now we actually have to go about combining this fully, which is kind of a pain in the ass, if I'm going to be honest. Okay, let's say that, let's call this 1, and let's call this 2, yeah? Just so I don't have to write out an extremely long expression each time. Expression 1, it's going to be h bar n pi times the exponential of I, and let's do h bar n pi minus pa, like that, inside the exponential as well. This times this, and then plus pa. Actually, do I want to do it that way? Or do I want to? Yeah, that's fine. I'll do it that way. Pa, and then the exponential I of h bar n pi minus pa over h bar. And then we're going to do minus h bar n pi minus pa, right? Yeah. Expression number 2 is going to be h bar n pi exponential of negative I h bar n pi plus pa over h bar minus pa exponential negative I h bar n pi plus pi divided by h bar. Is that still correct? Minus pa, yeah, and then minus h bar n pi plus pa. Okay, so thankfully these two cancel, at least. So what I'm left with, which is going back in blue, is going to be well, is there anything I can do to make this a little bit less painful to write out? Yeah, let's do a bit of, I'm gonna combine these two terms in a single by distributing out the h bar n pi. So that way we get exp of I h bar n pi minus pa over h bar plus, because these are adding together, right? Yeah. Plus exp negative I h bar n pi plus pa over h bar, like that. And we're gonna add pa and do the same distribution. Exp I h bar n pi minus pa all over h bar plus, or not plus, minus in this case, minus exponential negative I h bar n pi plus PA over h bar. Close that off, minus 2 h bar n pi, right? Just gonna double check my math really quick. I think that's correct. And now let me just use the line tool here and get the underside of this fraction. Take this, copy it down here. Okay, and keep in mind, this whole thing is just this blue part of this expression. So the phi term still has everything here in front of it. But for now, we want to keep on simplifying this down as much as we can. And at this point, is there anything else that we can do? This is E over this. Negative IPA. Oh yeah, okay. So if you look at here, so technically these expressions can be split further into two separate complex exponentials, right? So something like this, for example, this is actually a complex exponential of the first part of this fraction times the complex exponential of the second part of this fraction. So if you look at it, there's an there's a negative IPA over h bar for each of these, right? Because this is, let me just write this out fully, actually, just so that you can see it. If you have, for example, exp I h bar n pi minus pa over h bar, like this, technically, this is equal to exp of I n pi minus IPA over h bar. Is that correct? H bar. Yeah, technically it becomes like this. And this is technically equal to just e to the I n pi multiplied by e to the negative IPA over h bar, right? So you can split up a complex exponential like this. And if you do it for each of these complex exponentials, what you'll see is that in each case, there's always a negative IPA over h bar in the latter term, right? I times negative PA over h bar, negative I times PA over h bar, I times negative PA over h bar, and negative I times PA over h bar. So what that tells you is that you can further distribute out an e to the negative IPA over h bar for each of these expressions. So if we do that, then we're going to get e to the negative IPA over h bar, and then this is going to be multiplied by h bar n pi times e to the I n pi for the first term, plus, oh, actually, let's do it that way, plus e to the negative I n pi for the second term, and then plus PA times, similarly, e to the I n pi minus, no, not minus. Yeah, minus e to the negative I n pi, like that. And then this is all bracketed in, minus 2 h bar n pi. And at the bottom, let's just write this out, h bar squared n squared pi squared minus p squared a squared. And at this point, well, this looks very similar to, you know, an expression that involves converting this back into sinusoids, right? Because we know that cosine of theta is equal to e to the I theta plus e to the negative I theta divided by 2, and we know that sine is equal to e to the I theta minus e to the negative I theta over 2 theta, or 2i, sorry. So if you look at that, right, we have a very convenient expression here that allows us to reconvert it back to sines and cosines. This might seem a little bit unintuitive off the top of your head, because why would you convert it back to a sinusoid when you just converted from sinusoids to complex exponentials earlier, right? And you also have this complex exponential here. So like, I can kind of understand like that there can be some confusion where some people will be like, you know, why would I go through the trouble of doing that when I've already gone through all this trouble just to convert this into an expression that's purely complex exponentials? And the reason why is because you have an n term here, right? This expression is going to give you something like sine of n pi and cosine of n pi in both cases, right? Because your theta in this case is equal to basically n pi. So what's going to happen is that, you know, n is your energy level. It's a constant, right? It equals 1, 2, 3, 4, 5, 6, 7, and so on, depending on the energy level of your system. So you're going to result in an expression that is going to be like cosine of pi, 2 pi, 3 pi, 4 pi, and sine of pi, 2 pi, 3 pi, 4 pi. And those expressions can then be further simplified into just numbers. So because of that, we have an opportunity here to just get rid of these complex exponential expressions entirely. So that's exactly what we're going to do, right? So this is going to equal e to the negative IPA over h bar, and then multiplied by, let's see, this term is a plus, right? E to the in pi plus e to the negative in pi, which is this expression right here. Multiply the 2 over, so this is going to give us 2 h bar n pi cosine of n pi. Similarly, on the other side, this is going to give us PA, this is going to give us 2I PA sine of n pi minus 2 h bar n pi divided by h bar squared n squared pi squared minus p squared a squared, right? And at this point, well, I know that sine of n pi is always going to be 0, right? Sine of pi, 2 pi, 3 pi, 4 pi, etc., because n is equal to 1, 2, 3, etc. Because of that, the sine term automatically goes to 0. Cosine is going to alternate between -1 and 1, so this term is actually equal to just -1 to the power of n, right? In which case, if we plug that back in, we get a significantly more simple expression, e to the negative IPA over h bar multiplied by 2 h bar n pi times -1 to the power of n minus 2 h bar n pi, all divided by h bar squared n squared pi squared minus p squared a squared. And now if we then take this and go all the way back up, right, and get our original expression for phi and plug this new simplified expression in, now we have some more simplifying to do. Immediately, I see that we can take this 2 h bar n pi, and also let's get rid of these brackets because this is no longer a multiple term expression. This is now just e to the negative IPA over h bar times 2 pi n h bar times -1 to the power of n minus 2 h bar n pi. Right? So we can distribute out another unit of 2 h bar n pi, in which case we're going to get that phi is equal to negative h bar a times 2 h bar n pi divided by 2 square root of pi h bar a. And then our complex exponential, negative I n squared pi squared h bar over 2m a squared times time. And then what we're left with is e to the negative IPA over h bar times -1 to the power of n minus 1 divided by h bar squared n squared pi squared minus p squared a squared, like that. And let's now simplify this a little bit. Go. Okay, so the 2's cancel out. And let's make this phi is equal to, let's see, negative h bar squared, and then root h bar at the bottom. That's going to give you h bar root h bar, like that. You're going to get a root a on top after canceling out the a, and then you're going to get an n, and then the pi is going to give you a root pi, like that, right? So that's going to give you, what, negative h bar n square root of h bar a pi, like that, as a constant in the front. Copy over the complex exponential and all of this. And with that, we are done with part A. This is just your expression for phi. Okay, part B has multiple portions, so let's just do them one by one while ignoring the stuff below so that we don't get overwhelmed. First part, find the probability density, magnitude squared of phi. So ignore everything else, let's just do that first. Magnitude of phi squared is going to equal, the minus cancels, h bar squared n squared times pi h bar a. This complex exponential goes away when you take the magnitude squared, leaving you with, at the top, let's do this in big brackets, e to the negative ipa over h bar times negative 1 to the power of n minus 1, multiplied by e to the positive ipa over h bar negative 1 to the power of n minus 1. At the bottom, you have n squared, pi squared, h bar squared minus p squared, a squared, squared. Okay, let's mark this expression in red and let's focus on only this expression, right? So what is this going to equal? Well, if we distribute this out, this is going to be first term, the e and the positives, the negative and the positive exponentials cancels out. So you have negative 1 to the power of n times negative 1 to the power of n, which is negative 1 to the power of 2n, right? This is going to subtract by e to the negative ipa over h bar times negative 1 to the power of n minus e to the positive ipa over h bar times negative 1 to the power of n plus 1. 2n is always going to be an even number, so this term is just going to be 1. So 1 plus 1 makes 2. You have 2 minus e to the negative ipa over h bar times the negative 1 to the power of n minus e to the ipa over h bar times negative 1 to the power of n. Let's distribute this out, and my mouse is stuck under my desk. Please give me 1 second. It is causing me a bit of an issue trying to get the scroll wheel working. This is going to be 2 minus negative 1 to the power of n times e to the negative ipa over h bar plus e to the ipa over h bar, right? Is that correct? The negative 1 factors out the negatives in this case. Yeah, and this can then be turned into a sinusoid, right? Because we know that cosine of theta is equal to e to the I theta plus e to the negative I theta divided by 2, in which case the theta in this case is going to equal PA over h bar. So you have 2 minus negative 1 to the power of n times 2 times cosine of PA over h bar. Okay, now let's factor out the 2, in which case this is going to become 2, 1 minus negative 1 to the power of n cosine PA over h bar. Now let's go back to the top and take this, copy it, move it over like this, and then attach this expression to the front. In which case, rewriting this a little bit more formally, magnitude phi squared is equal to 2h bar cubed n squared pi a times 1 minus negative 1 to the power of n cosine PA over h bar, like that. Let me just double check to make sure that I'm not missing any. Oh, I almost forgot the bottom. That would have been very bad. Let's do that. And let's just cover this. There we go. Okay, double checking again, just to need to make sure that this is actually all correct. N squared pi squared 2 h bar cubed n squared pi a1 minus negative 1 to the power of n cosine pa over h bar. If it's even, then it becomes plus. If it's odd, it becomes plus. If it's even, it becomes... Yeah, that's correct. Okay, so that's the first part. Now let's move on to part 2. Okay, so now at this point, we have the probability density, mag phi squared. We now want to graph this function. Now, you have a lot of constant terms in this expression, and if I was to go to Desmos and I try to just write this out and try to graph it, Desmos is going to give me an error because of the fact that I have way too many variables here that aren't explained for. So what we're going to try to do is we're going to try and rewrite this expression and maybe massage it a bit so that instead of having all these constants, h bar and a particularly, we're going to try to get them all to sort of go away or try to hide them inside a greater variable. And immediately if I look at this, right, this is phi in terms of p, and I have a cosine of pa over h bar here. So what this suggests is that maybe I want to define a new variable. I want to call it gamma, and I'm going to say that it's equal to pa over h bar, in which case my goal now is to get as many terms in terms of pa over h bar as possible. And from there, maybe I could possibly, get this into something that is in terms of purely gamma while hiding all the h bars and the p's, or h bars and the a's and the p's inside that gamma expression, right? So if there's a pa over h bar on top here, I look down at the bottom here and immediately I notice, hey, I can take out an h bar here, in which case if I do that, this becomes a p squared a squared over h bar squared like this, right? So in that case, similarly, I have a gamma here and I have a gamma squared here. So that means that mag phi squared is now equal to the h bar is, oh, sorry, this is h bar squared. Is that correct? No, it should be in... Hang on, I'm having a bit of a brain fart right now. Sorry. Yeah, that should be an h bar squared. And since there's a square in front here, it's going to get doubled again to h bar 4. In which case, that's going to give you 2n squared pi a times 1 minus negative 1 n cosine pa over h bar, which I'm actually just going to preemptively call gamma, divided by h bar n squared pi squared minus gamma squared, like that. And now what you can do is I can say, okay, well, I know that a and h bar are constants, right? So what's stopping me from moving them to the other side and saying, okay, I can redefine this expression as h bar over a times mag phi squared is going to equal, 2 pi 1 minus negative 1 n cosine gamma, all divided by n squared. Pi squared minus gamma squared, like this, right? There's nothing stopping me from this. And what I can say is that this term is just going to become some constant ratio factor, right? It's just going to become some c that's multiplied to my expression. And if I'm going to do that, well, there's nothing stopping me from also taking this 2 pi and moving it into the constant as well, right? If I divide a constant by 1 over 2, or if I multiply a constant by 1 over 2 pi, it's still going to be some kind of constant. So now I'm just having some arbitrary constant which can determine the scaling of the graph. And I can control what that constant is. I can, slide it up and down on the slider on Desmos until my graph is actually visible, because otherwise you're probably going to end up with like a graph that's very close to the zero and very spread out. So maybe we have this constant and we arbitrarily define it as some number so that we can get a graph that's actually readable. And then the rest here is just an expression purely in terms of gamma. And this is much easier to actually graph in Desmos. So I'm going to go into Desmos and actually graph these out individually, and then I'm going to attach them on at the bottom after I do this cut. Okay, so we are asked to graph this function for n equals 1, 2, 5, and 10. I've gone into Desmos and just graphed this. I keep in mind that if you want to do this for yourself, the constant at the front, you have to sort of, I have had to make it increasingly large as n gets larger and larger. And the reason why is because if you don't do that, the graph becomes extremely flat at higher n values. And what will happen is, without increasing the constant ratio at the front, just like increasingly more and more and more so that like you can make the graph look bigger, the graph gets smaller until eventually it's indistinguishable for all intents and purposes from just like a flat line. So because of that, for n equals 1, I was able to get like a very nice curve just by setting c equal to like 150. But like as I got farther and farther down into n equals 2, n equals 5, n equals 10, by n equals 10, I had to have like a constant that was like in like the hundreds of thousands. Just to make it so that I could actually get like a visible spectrum here. So do not, take these grid values for like a grain of salt. They're not entirely accurate. Realistically, the actual n equals 10 expression is going to be super flat if you're graphing, c times magnitude phi squared. But that being said, just looking at the shape of the graph, what you'll see is that for the first energy state, you have a bell curve for the possible values of p, right? As you go into 2, it gains 2 curves with a 0 in the middle. As you go to 5, you get a bunch of small curves in the middle and 2 big curves on the edges. And you get to 10, you see the same thing, but just more pronounced, right? So what happens as you go from, n equals some finite value to n equals infinity is what's going to happen is that the bottom, the inside is going to get flatter and flatter. So the possible momentum is going to get very peakly skewed about like the 2 extreme values. And if you think about this mechanically, right, as the energy in this well gets larger and the ball starts, bouncing left and right super, super fast, the possible velocity of the ball starts to approach sort of the edge limit for the box, where like if it gets to this point and if it gets past this point, it's going to escape the infinite square well, or it can't really escape an infinite square well. But if you were dealing with like a finite square well, right, you're hypothetically approaching the limit of velocity for which you could then have the particle escape the square well and become a free particle. And these peaks are characterizing sort of that critical point in the velocity, where at that point, once you get past that point, the particle escapes the well and changes from a fixed particle inside the stationary square well into a free particle with an actual determinate velocity. We can actually look at this mathematically if we take this expression, right? So we have the original magnitude phi squared term right here, and I'm going to look at this one. Actually, no, let's look at the whole thing. I think it's better if we look at the whole thing. If you look at this, what you initially see is that, okay, I have an n squared term here, and then I have an n squared square term at the bottom. So this is, sort of proportional to like n squared over n4, right? So as n goes to infinity, you sort of expect, oh, this is going to go to 0 because you have an n to the 4 at the bottom and n squared at the top. The n to the 4 grows way faster. However, keep in mind that you have a hole here, right, where if n squared pi squared is equal to p squared a squared over h bar squared, this term here is going to become 0, in which case you have a 0 at the bottom, and then some finite term on top, which is going to go to infinity, right? So in that case, as we go to infinite energy, the momentum of the wave function is going to approach a specific value, which in this case is going to be p squared such that p squared a squared over h bar is equal to n squared pi squared. And this is actually exactly equivalent to the classical mechanical result, where we know that the energy of the infinite square well is equal to n squared pi squared h bar squared over 2m a squared, right? And earlier on in like chapter 2, we showed that, hey, you know, if I set this equal to the classical 1/2 mv squared, and I say, okay, I replace mv squared in terms of p, well, I know that, you know, p squared over m is going to equal mv squared, right? So if I set this, then this is going to be equal to n squared pi squared h bar squared over 2m a squared is equal to 1 over 1/2 times, well, that's p squared over m, so p squared over 2m, like that. And if you cancel this out, well, the 2m cancels here and the 2m cancels here. What you're left with is p squared is equal to n squared pi squared h bar squared over a squared, which means that if you rearrange this, you get p squared a squared over h bar squared is equal to n squared pi squared. And that's exactly what we have over here. So that's a very good thing. That implies that, you know, sort of this treatment agrees with the classical mechanical result of what the expected momentum would be in infinite square well. So given that, we can be sort of reasonably confident that this is sort of what it approaches as n goes to infinity. Now, finally, we're asked to compare our answer to problem 3.10. And 3.10 was basically asking you, hey, is p determinate in the infinite square well? And what you found in 3.10, and if you don't remember that, feel free to go back and look at that problem 3.10 video. What we found is that for the infinite square well, p is indeterminate. Which means that p does not take on a specific value like energy does, right? Instead, it takes on a range of energy, and we're seeing that exactly with this, right? We have a probability density for p. And what's going to happen is that at lower energy states, you have very blurry p wave functions, where you have this very well-defined bell curve where p is very well spread out, right? There's a very equal probability, relatively speaking at least, of finding p taking on any given value in a given range inside of our infinite square well. But what happens as n gets larger and larger is that the probability of finding a particle in the infinite square well with momentum in this middle range basically goes down to 0, and the probability basically peaks towards finding it either with a positive velocity p or a negative velocity p, which is approaching basically what would be the escape velocity required for the particle to escape the well and then become a free particle, which results in p then taking on a determinate value, right? Because we found also that a free particle actually has determinate values for p, whereas it has indeterminate values for x. So that would just give you the classical mechanical momentum expression, right? Where the moment p becomes the classical mechanical momentum expression, that's sort of the critical point, where as soon as you go above that, the particle is going to escape your well, and then you're going to have a free particle. And with that, we are done with part 2. Okay, C is either going to be extremely simple or pretty difficult, depending on if you're going to use a calculator for this expression or not. You are told to calculate the expectation value of p squared using the momentum space wave function for the infinite square well. So we have magnitude phi squared, in which case p squared momentum is just going to be, you know, the integral from negative infinity to infinity of 2n squared pi a over h bar times n squared pi squared minus p squared a squared over h bar squared times 1 minus -1 n cosine p a over h bar. And since in momentum space the operator p is just p, right? We're going to add a piece. We're just going to add a p squared at the front like this and close this entire expression in terms of dp. This expression, if you want to solve it, requires contour integration and like Cauchy integrals, which I believe at this point in the textbook, and like considering the level of math that you would be expected to have for this point in the textbook, is a little bit too high, and I would just recommend you plugging this into an integral calculator to find the answer. because the answer is just going to end up being n pi h bar over a squared if you plug it in correctly. And when they say to compare your answer to problem 2.4, 2.4 is asking you to calculate the expectation value of p squared for the infinite square well, but in position space. And in problem 2.4, you found that the expectation value of p squared was exactly equal to this. So this does agree. The problem is just doing the integral. If you want to like sort of get an idea of how to start it, what you would do is you would redefine, gamma again equals PA over H bar to just try to get rid of as many constants as you can, and then rewrite this expression in terms of d gamma instead of dp. And then from there, you would get this complicated expression that requires contour integration or Cauchy integrals or however, some other, calculus 3 level technique in order to actually solve it. And in my opinion, I don't think that's something I want to focus on because that's going more into math instead of sort of the physics I want to cover. So I'm just going to say plug this into a calculator. If you actually want to solve it, then you're going to have to learn Cauchy integration, Cauchy integrals and contour integration, all that stuff that you would learn in Calc 3. Which, if you want to do that, by all means, go ahead. I don't really want to focus on that. It's a level too high for me to care about doing it at this point in the textbook. Maybe if I was covering like a later chapter in the book that actually uses this kind of technique a lot more in depth, I might consider actually going over it and going through it in more detail. But at least for this lower point in chapter 3, where sort of if you were taking this in like actually college, you wouldn't, at this point in the textbook, I don't think you would be at the level of like a Calc 3 course yet. So I'm just going to skip over it. And I'm going to say use a calculator or figure out how to solve it yourself if you want to dip your toes into using, those types of techniques for this textbook at this point in time.